So very warm welcome to everyone in the SMaRT seminar series today. So this is our last seminar for the year, and it's my utmost pleasure to introduce Professor Alice Cicirello to this last seminar with which we are ending the series this year. She's an university assistant professor in applied mechanics at the University of Cambridge and also a fellow of the Churchill College. She leads the Data, Vibration and Uncertainty Group and is an executive board member of the European Association of Structural Dynamics. Her research sits at the intersection of applied mechanics, data-driven modeling, and uncertainty quantification, with a very strong emphasis on physics enhancing machine learning. Dr. Cicirello has held academic and research positions at various universities, including the Oxford University, TU Delft, and the Cambridge, and also has industry experience as a senior research scientist at SLB. She serves on multiple international journals' editorial boards and has played a leading role in organizing major workshops in the field of physics-informed machine learning series. With that brief introduction, please join me in welcoming Dr. Cicirello for this presentation. And with that, Dr. Cicirello, it's all yours. Thank you so much for giving us this presentation today.
Thank you so much for giving me the opportunity to present at this online seminar series. I'm very, very grateful for this. I'll dive in. So, okay. I'll start by telling you a bit about what we do in the Data, Vibration and Uncertainty group, because probably this will explain to you why we are approaching things in this way. So what you see on these slides are different types of structure. And if you think about it, what they have in common is that these are complex build-up structure and they're subject to broadband type of loading. When we think about the structure, what we can do is to use different kinds of modeling. We can use a single degrees of freedom model to complex, for instance, vibroacoustic model to multi-body dynamics models. And what we typically do for these structures, starting from the models, is also thinking about how to monitor this structure, how to collect information. And typically when we think about monitoring, we think about data, but the data is not just in terms of measurements on the structure. Data is also in terms of other type of information that come from inspection reports, failure reports, accident reports. And what I'm very interested and passionate about are actually three grand challenges. The first one is how do we design this complex build-up structure, considering that they are subject to uncertainties and nonlinearity? How do we monitor this structure and assess the remaining useful life, considering that we still have uncertainties and nonlinearity, but typically we are dealing with sparse and noisy data? And what I'm also very interested about is developing explainable and interpretable machine learning strategy that can be translated for engineering application. So how do we do that? Pretty much within my research group, we are looking at the problem from 4 different points of view. The first one is actually looking at laboratory experiments and building physics-based models. We also look at uncertainty quantification and manufacturing variability strategies. And then what we are looking at are ways of extracting information for different sources of data. And of course, the main goal then is to learn how to combine data, models, and knowledge. Now, when we think about the type of system that we are interested in and how we go about it, is that we go with this integrated approach that starts from the fundamental to all the way to physics enhanced machine learning. And that will be also the cover of today. And think about the system. We've been interested in covering systems like cars, satellite, but also wind turbines, ferry keys, key walls. We've been looking also at ways of going from text to models, looking at wearables failure, but also animals, and how to understand better how to monitor, how to sense, but also how to model and learn how animals communicate. And more recently, we've been looking also at climate. Okay. So this was just to give you an overall view of what we do in the DVU group. And now I'm going to discuss a bit more about what you will learn during this lecture and what you will hear during this lecture. First, I'm going to talk about uncertainties, and I'll focus on uncertainty in general, and then I'll talk about structural health monitoring. Later, I'm going to move to recent advances on physics-enhanced machine learning strategies that have been developed within the DVU group. And at the end, I will talk about open challenges and opportunities that are still there. Okay. So the most simple way that I typically use to connect with people and think about what are the biggest challenges that we have is thinking about decision making and guiding decision making. What we try to do with structural health monitoring is guiding this decision making. But before going into the actual structure, let's start with the low risk consequence decision making. Okay, so what you see on the screen is a screenshot of my phone, and in that case, I'm using WhatsApp. And I start writing, today I will give up. And you can see that there are different options given there, talk, call, seminar. Now, if I start adding S, you will see that instead of going, towards the word seminar, it's actually getting confused. But I was giving more information. So why is it getting confused? Well, some of you might have noticed, I'm Italian, very Italian. And actually, I was using the Italian keyboard while I was writing in English. So in a way, I was using bias data for a model that was built on Italian language in the case. So you can watch it the other way around. I was using the wrong data for the right model. Yeah, it's either way. In this case, I was trying to get something in English, so it was the bias data. Okay, so if we think about then another type of problem that we have is, for instance, again, my phone, and I'm looking at Netflix, and I created a new account, and I started looking at things that I like, actually selecting things that I like, and then I want to go and look and watch Memento. This is one of my favorite movies of all time, and I know that. But if I check what it says, is that there is only 61% match that I will like this. And this is actually because I had little data, and there were very little data because it was a new profile. Now, typically those two conditions, the bias data and the limited data, are very common in engineering. Now, if I'm looking at this low risk consequence that you see on the screen, it's very easy for me to actually guide my decision making and, for instance, watch Memento, or for instance, know that I'm not gonna give a sleep. But those are very low risk. But can we then think about using only data to actually guide decision making when we are thinking about complex structure? And if we say data, what data should we use? And again, I use this example just to make this point hopefully very clear. And now we should talk about what type of data we have. And in the example that I gave you, the data was movies or it was words. But in engineering, we are typically dealing with expensive music and noise. And I'm going to explain what I mean by that. Data is expensive to acquire in engineering, and it's also typically multimodal. It comes in different forms, collected in different frequency. And by multimodal, in this case, I mean information coming from text, from simulation, from experiments. It can be uncertain, it can be sparse, typically it's incomplete, we don't have all the conditions, and it might be even corrupted by confounding influence, the effect of other things that will happen in our measurements that are not coming just, for instance, the vibration response caused by operational conditions, but it might come from, for instance, other environmental conditions. And that's the music part, but also there is noise in it. And in this case, the noise is coming from the no-smoothness that we sometimes have in the data. So for instance, you can see here what I mean by that, in which we have sharp variation of the response. And the fact that typically we are not necessarily able to observe directly the phenomena that we are interested in. For instance, it's difficult for us to observe friction at the joint, but we can observe the effect of that. Similarly, if you think about damage, we can observe the effect, but not the damage itself directly most of the time. What it means is also that we are dealing with direct measurements, and sometimes we don't have just enough information coming from measurement itself, and we have also simulated data that can look at extreme events or other conditions that maybe it's difficult to obtain from the structure. And indeed, extreme events are coming as well. So yeah, expensive music and noise. Okay. When we think about data, this data is actually also connected, and that's what we have to think about. And data is not enough in the sense that it should be transformed in this relevant information. But every time we are talking about data, we are actually all the time making some inherent assumption. And this inherent assumption can be quite dangerous if we forget about them. The first thing that we are thinking of is that the data that we have is informative. And this is not necessarily the case all the time. We are also assuming that the data is accurate and that the data is reliable. Now, why this is important is that if we are deciding to use, for instance, a data-driven model and guide our decision-making based on data, the results will be as good as the data. And what it means is also that we should be able to observe all conditions, and this can be very difficult, and maybe we should also be able to have labels for all these conditions. But also we have to remember that our data should be up to date. For instance, we are looking at a bridge or we are looking at a wind turbine and there have been maintenance activities. Can we still use the data from before? Because now the data is not up to date, given that that's the new structure. How are we going to use the data and for what task will become very important. Trusting the quality of the data is also very important. We have to remember that we're always dealing with sensor, and this sensor can be actually damaged or can be affected by environmental condition. And also the way in which the data should be collected should be done in a consistent way. As I mentioned also briefly earlier, we can have confounding sources, so that what we are measuring is not just the quantity that we think of, it's actually the results of something else. And having metadata about the information that we are collecting or how the information is collected is also extremely key. So in a nutshell, then, what we're trying to do is guiding decision-making. So for instance, preventive action to restore normal condition in engineering, which means that we are dealing with high-risk consequences. They are not just low-risk consequences, like the one that I showed you before. And what it means is that we have to go beyond the data that we have. And again, the main challenge is that we actually measure the effect, the response actually, and not the cause, so for instance, the damage. So when we think about how we handle the problem, we typically use measurement of some outputs or some behavior. And what we try to do then is to go backwards, and we do an inverse type of approach in which we are trying to combine this data with physics or with physics data knowledge model. And what we want to do is to learn something. We would like to learn model or latent parameters to make inference or to make safety assessment. And again, this is a sort of inverse model problem that is very difficult because typically it's not unique. So when I was mentioning this, I told you about physics or physics data model, but let's take a step back first, and let's compare two different types of strategies, just to make sure that I'm giving to you all the information that you need to understand the next step. So the first step, the first strategy that I'm going to talk about are physics-based type of strategy. And typically what we have is that we have some input data and we have an algorithm. And then we have a causal model that basically is telling me, given this input, that's the output that you will get. And the output is typically a physical quantity. And this algorithm is actually embedding, has an explicit relationship between cause and effect. Now, the main difference where we are now using a data-driven type of approach is that we are using the input and the output data to learn an algorithm. And this algorithm is going to be able to solve a specific task. It can be regression, classification, clustering. And if you learn one task, the algorithm cannot directly be used for something else. So we will have to learn a different algorithm. So there are some choices that we have to make when we do data-driven strategies, and these choices then will affect, and I'll try to use this sort of schematic to tell you more about the uncertainty that come when we are thinking about data-driven strategies, to then talk more about the uncertainties directly into structural health monitoring for a system point of view. So let me guide you through this. So what I told you is that with machine learning, we have input data, output data, and we get an algorithm. First of all, what data should we use? That's the first question that we should ask ourselves. Now, when we are thinking about the algorithm, we're going to build a data-driven model. This data-driven model will be a function of these input and output data, but we'll have also some parameters. And these parameters are parameters we don't know, so they are latent. And these need to be either specified or optimized. We should learn them. So we have two questions, actually three questions. What data, what model, what parameters? Those are the first choices that we have to make. Now, when we think about what data, we have to think about the uncertainties that come with that question. And the uncertainty is that typically the data that we are dealing with has some inherent variability. And what it means is that we are dealing with some aleatory uncertainties. And the first challenge that we have is thinking about, do we have enough informative data? Now, when we think about the data-driven model instead, we are thinking about different type of uncertainties. The first uncertainties is so-called epistemic uncertainties. We are dealing with a model discrepancy, and this model discrepancy can come from two reasons. The first reason is that our model is based on the data. And this data is going to be affected by some aleatoric uncertainties. And we can also have some corrupted or non-informative data, as I was mentioning to you earlier. Now, if we think about the model instead, the model can come from a wrong model architecture. I didn't tell you yet what kind of architecture I'm using, and I did it on purpose, because independently of that, you might choose an architecture that is not the best to represent the phenomena. But you might also have some challenges determining the correct model parameters. And this is now becoming an uncertainties that come from the data-driven model. All of these uncertainties that are coming in the data-driven architecture might limit the applicability of machine learning in guiding decision-making in engineering. Again, we start from the data and we go to the model. But there are other challenges that we have to think about. The first one is that how do we cope with these uncertainties? Can the model that we're going to develop generalize to unseen inputs? Because again, these are all linked challenges. And the challenge 4 is that can the model be explainable and interpretable? And I'll tell you in a bit what I mean by that. Okay, well, I told you about the uncertainties and the uncertainty that come when we think about a data-driven architecture, but we are interested in a system, in an engineering system. And we can think about the problem and the definition of uncertainty from a system point of view. And this is also very interesting because you will see how the different uncertainties and model parameters are becoming also important, and those definitions become important. First of all, what you see on these slides is an input-output type of system S, for which we could have some model, and it's described by some states, and we can have some parameters of this model. And what you see also are disturbances acting on the system. And what you see here are these quantities that can be measurable via monitoring. Okay, so when we think about the uncertainties, of course, we have to think about input uncertainties and inherent variability, for instance, in the loading of the system. We're going to have inherent variability when we think about disturbances, and we have to deal with model form, what type of model we're going to use for the system, the model parameter of uncertainties. What we have to deal with is also domain knowledge and how we deal with uncertainties on the things that we don't know. For instance, if we think about a structure, frictional model, what frictional model should we use? And we have to always remember that when we build this model, we are also going to solve them, and we're going to have a solver code uncertainties that we should handle. Okay, now I told you about the sort of inherent variability, model form, domain knowledge, and solver, but then there is also the output. We're going to measure something, and we're going to have measurement error, spatial and temporal correlation, gap disperse measurements that we have to deal with. And of course, as I told you at the beginning, I'm also interested in this complex structure that are subject to broadband loading. And what it means also is that a broadband frequency range is typically involved when we think about the response. And what it means is that small manufacturing variability or part-to-part variability will become explicitly important, and we should account for that. So spatial and part-to-part variability will play a role. Okay. So all of this to tell you about uncertainties and the different aspects of uncertainties, but why they are so important? Well, it's because typically in engineering, we are interested in something that is called explainability and something else that is called interpretability. So let me walk you through what I mean by that. So interpretability is actually trying to answer the question, how was a prediction made? And explainability instead is answering the question, can we communicate the prediction to support decision making? Okay, so what's the difference there? Interpretability actually boils down to understanding if the model is going to fail or succeed to complete the task. Do we understand why that is happening, basically? And this is very important because from the modeling point of view, we will trust more something that if something goes wrong, we will understand what is happening. So if we have a physics-based model, we might understand that we made some inherent assumption. For instance, we assumed that the system was linear time invariant. Well, if we think about a data-driven technique, it's more difficult to understand why the model will fail to complete a task, because there are many aspects that can be there. As I was mentioning to you, there are all these different uncertainties coming in. Now, thinking about explainability instead, the communication part to guide decision-making doesn't mean only that the results should be comprehensible. It means also that we should be able to quantify any remaining uncertainties in the prediction. And again, this is important for the decision-making point of view, because we should be able to present it in a way that should be understandable, but also understanding how critical the decision will be and what will be the risk associated, for instance, in not taking that kind of decision. Okay. So what it means and what I'm trying to lead into is the fact that just by using physics or data-driven techniques is not enough. And typically what we are interested in is in tackling these very, very difficult and very exciting challenges by combining physics, data, and knowledge. And this is actually a very difficult integration, because what we're interested in is not just combining mathematical models, a physics-based model we developed, with data that we have, is actually combining also domain knowledge, prior knowledge, computational strategies with multi-fidelity data. But what it means also, as I mentioned to you briefly, is that we should deal also with wrong physics model biases, maybe wrong assumption that we made on the physics part. We should deal with corrupted data. We should deal with non-informative data, and especially dealing with uncertainties. Uncertainties is becoming, and it is one of the biggest challenges. And of course, we should be able to provide strategy for validating the solver in different tasks, basically. Now, if you're thinking now about how much physics versus data should be included, well, there is not just an answer, and it really depends on your preference or where you start or where you sit, but typically is also based on what information that you have available. So we can start, for instance, thinking about the fact that we have lots of physics knowledge, and now we are collecting information. And what we have there is a physics-based model, I'll call that G, in which we have some model inputs and some model parameters. And now we are adding biases that come, for instance, from the data, from the domain knowledge, and we're building a new model M. And this is a sort of physics-guided strategy. We can also go from the data-driven versus the physics. And what it means is that we're going to have our data-driven model D that is built based on measured input and output and some parameters. And now we have biases, and these biases can come in different forms and may come from physics, for example. And these help us going from the data-driven part towards the physics. Of course, what we can have is also a merge of these two, in which we are learning also somewhat at the same level, both the physics and the data, and we are adding also physics biases. And this is somewhat called physics encoded machine learning. So now this definition or not strict definition, and actually there are many excellent researchers around the world that are using different definitions. These are the ones that I found it easy, and I found it easy for me to explain where we go, where we start from, and where we're trying to aim. But there are different definitions. As I was telling you, sometimes they're called gray box model. It's a definition of a spectrum as well. This might be called also scientific machine learning. And sometimes what is happening is that it's also called with a much more engaging name. Sometimes there is AI for science or science for AI. And but again, nomenclature matter just a little bit. It's just to give you an idea. When I talk about physics guided, I start from a physics-based model, and I'm adding data. When I'm talking about physics informed, I start from a data-driven model architecture. Okay, I told you though that I'm using biases. So what do I mean by biases? So in this case, are good biases. And what we're trying to do basically is to say, although the data is telling us something, we would like to add some constraints, some information that help us focusing in some region of the domain. And this information may be expressed in terms of physics and domain. And they might come into our architecture at different levels, not just in the loss function. That might come by introducing data that embody the underlying physics. And this might be obtained by lab experiments or by building simulation, basically. We can have inductive biases that actually are looking at incorporating prior assumption and physical constraint. So it can be, for instance, reciprocity law, invariances, boundaries, or other laws that you know of. We can have also a learning bias, which basically it's talking about how we are gonna use the learning and inference algorithm for our task, basically. And what it means is what loss function, optimization, and algorithm constraints are we going to use. And another bias that to me is very interesting is the model form discrepancy bias. It's how we include terms that actually embody the model form and basically or partial knowledge of our system. Pretty much what I'm saying is that if we know very well the linear part, we don't have to relearn that. We can actually feed it into the system in our learning algorithm. And you will see later what I mean by that. So basically, all of these biases are helping us constraining the space of admissible solution. And by combining them, they will help us accelerating training because we're now focusing on a space, on just a space of the entire domain. And this should help us reduce computational cost, energy consumption, and enhance generalization, even if we have limited data. And of course, as I mentioned, they can be introduced in different parts of the algorithm. So what is then physics-enhanced machine learning doing? Or what are the goals? Well, first of all, we would like to avoid poor generalization to unseen condition. We would like to remove physically inconsistent or implausible prediction, even if we have limited data. And we would like to account for uncertainties. And as I told you, uncertainty comes in the physics, in the data, in the parameter, in the model form, can be reducible, irreducible, and they can be solver code uncertainties. At the end, what we would like to provide are explainable and interpretable fast and accurate solutions that can extrapolate to unseen condition in the data. And what it means is that we would like to learn something that we didn't know before. It can be like informing physics, like identifying an unknown constitutive law, or governing a question, or identifying reduced order models, or the experiments that we would like to carry out. So big ambition for physics-enhanced machine learning. Now, I told you about, we can start from physics or data, but now this also begs the question, which physics-enhanced machine learning strategy should we use? Well, there is no one-size-fits-all, and the way I try to think about this, it really depends on the amount of physics knowledge versus informative data that you have. What's the purpose? What's the task? And what's the complexity of the system that you're trying to learn from? And so if you think about the amount of physics versus informative data, I already sort of give you hints about that. We can start from a physics-guided or a physics-enhanced probabilistic machine learning technique if we start from lots of physics and less data, or we can go to the extreme in which we go from a sort of physics-informed or a physics-enhanced, for instance, neural network architecture. If you think about purpose, depending on which type of task that we would like to solve, we might want to look at accelerating solver and accounting for uncertainties, or we might want to identify enough physics terms or developing digital twin. Each task will require a different type of architecture. And of course, depending on the complexity of the system that we would like to capture, our assumption, our model, our data will be different. And sometimes we can get away by saying, okay, we can assume that the model can be linear time invariant, the system can be assumed like a linear time invariant, or we actually have to deal with multi-scale, multi-physics, and linear time varying dynamical systems. Okay, so this was a sort of big way to describe uncertainty in SHM and describing physics-enhanced machine learning in general as a brief intro, and I hope that was clear. And now I'm going to move on into approaches that have been developed within the group, especially with the aim of guiding decision-making under uncertainties. Okay. I'm going to start with a very well-known physics data nodule integration that we use in structural health monitoring. And this is actually Bayesian model updating. It's a physics-guided machine learning technique, if you think about it, because what we're trying to do is to actually start from the prior and the likelihood we would like to learn the posterior. Now, the prior is actually representing our prior knowledge on some uncertain input parameters. And this prior knowledge comes from expert opinion, physical constraint, prior data. And it is on parameters that we cannot directly observe. Okay. Now, when we build a likelihood, typically what we do is that we are looking at a discrepancy because between observed informative data and a model prediction. So we are inherently assuming that we have a non-physics-based model and that we have access to some noisy dynamic measurement response. And what we're trying to do then is that we are going to use this prior and this likelihood to get the posterior. Now, what it means is that the results of Bayesian model updating are very sensitive to the prior distribution assumption, to the likelihood assumption that we're going to do, so how we are going to describe this discrepancy between the observed informative data and model prediction, but also will depend on the computational strategy to obtain the posterior. I'm not going to talk about the computational strategy. I'm going to focus on two challenges. First, I'm going to describe the likelihood assumption, and then I'm going to talk about the prior distribution assumption. Okay, so challenge one in SHM. So most of the time with the data that we are going to deal with are actually coming to us, not in a form that can be assumed like IID. And what I mean by that is that are independent and identically distributed. Most of the time, the data that we have are actually spatially and temporal correlated. This is because they come from real sensor. And what you see, for instance, here is a bridge in which we have actually measurement of different spatial information. And what we typically have access to when we're dealing with this type of system are this physics-based model, and we have these measurements. But the information on these measurements, again, are not uncorrelated. We cannot assume that they are uncorrelated. And what we would like to do is actually accounting for the spatial and temporal correlation, because if we don't do so, we're going to get the wrong posterior distribution. So how can we do that? Well, first of all, we can start with a model from bias because we know the physics-based model that we're going to deal with. And we can look at a large number of noisy measurements that are available because we are collecting information along very many different points. But what we can do now is adding inductive biases. We can look at a pool of candidate models that can describe the spatial correlation. Now, if you want to deal with this type of problem, it's going to be very, very difficult to do so. And in fact, it seems very trivial, but in order to solve this type of problem, we have to develop an efficient calculation of the log likelihood strategies. And this can help us to deal with large data set. And now what we can do with that is that we can look at a candidate model pool, and we can actually then obtain through bias rule a posterior predicted, and through nested sampling in this case, a posterior predicted distribution that actually now is representative the correct latent parameters. To do so, now we have to make some assumption. And what we did was assuming that we have a Gaussian model prediction error. This is a typical assumption, but it's not necessarily all the time correct. So what you're going to notice is that every time I'm going to talk of some of the technique, I'm going to give you some sort of description of the technique, and I'm going to tell you about which are still the shortcomings being there. Okay. Another challenge is that we are very interested in structural monitoring is actually the fact that we are dealing typically with, most of the time, with limited data at the beginning, and we don't have much knowledge on the prior distribution. So we are going out the other extreme now. So we have very limited knowledge on the prior of these latent parameters, and now we have limited data. And what we would like to understand is can we obtain a robust posterior distribution. And we define robustness as a metric that is based on the posterior sensitivity to the assumption on the prior distribution. And what you see here are an optimal prior and a worst case prior. So let me basically walk you through what I mean by that. We are looking at prior distribution that either maximize or minimize a certain metric that is based on the posterior. And what you see on this graph are a nominal initial prior distribution, what we assume at the beginning. And then we have a final approximation to the posterior distribution and a final prior that will be can be the optimal prior or the worst case prior. So we don't know the optimal prior and the worst case prior. That's something that we don't know. And actually, we would like to understand how the choice on the prior would affect the resulting posterior. Again, we are dealing with limited knowledge and limited data. And this is not a standard Bayesian model updating. And in fact, we are looking at robustness. So to deal with this problem, we develop a technique that is a physics-enhanced machine learning technique, again, in which we are combining physics, data, and domain knowledge in different form. The first thing that we have to do was actually describing uncertainty in the prior distribution, and we did so by using an ambiguity set. An ambiguity set is a set of distributions that are not far from the reference nominal distribution in some statistical distance sense. And what it means is that an ambiguity is defined in terms of this radius, epsilon, and a nominal distribution p. And we have some properties. We're gonna look at any distribution that is contained in the ambiguity set, and we have to define a statistical distance. And in this case, we're gonna use the Wasserstein distance to do so. And we have to have two conditions that are going to be met all the time. And basically, the reason why we define this ambiguity set is to restrict the space of distribution that the prior distribution could take, basically. Okay, so how do we handle this? Again, as I was telling you, we are combining physics and domain knowledge, and you can see here what I mean by that. We have a physics-based model. We have to make some assumption about the likelihood. We are going to use experimental data. We have to define an ambiguity set, as I just told you, and we're going to use a Wasserstein distance. If you're wondering why we are using a Wasserstein distance, there is this W here, is because it does not have to be continuous with respect to a nominal distribution, and the distribution could not share the same support. And that's very, very important. Now, what we have to do is looking at this optimization of a chosen functional. And as I told you, what we are interested in are the optimal and worst case prior and the approximation to the posterior. And the way in which we look at the functional approximation is that we look at the KL divergence of the unnormalized posterior and the approximation to the posterior. Now, this is a very interesting strategy, but we are making some assumption here, and we are assuming that the nominal prior distribution and the radius can be specified by the user. And again, this is a way in which we are trying to deal with some of the challenges that we are dealing with where we are looking at physics-guided machine learning strategies. You can find more information on this paper here about the strategy. Okay. Another challenges that we are typically dealing with is obtaining the measurements where we need them or when we want them. And typically these are measurements at inaccessible critical location. And the way in which we would like to do that is to look at what is called virtual sensing. And to do so, now we're going to move into physics encoded type of strategies. And we have applied and developed this technique to actually two different types of structures. We applied that to the Western mean part wind turbines data, and we applied this to also some fairy keys. You can see there the pictures of the people doing the work, but of course there are amazing collaborators also involved in this, and you can find more in the paper. And the idea there is to use what is called a Gaussian process latent force model to actually obtain this virtual sense or this critical location. So let me explain to you how we're going to use that. So the idea is that we're going to, for instance, look at measurements at A1, A2, and A3. And what we would like to get out of this are measurements at S2, S3, S4, S5, 6, and 7. Now, the catch is that A1, A2, A3 are acceleration measurements, and we are looking at strain instead from S2 to S7. So how do we combine data, physics, and knowledge in a way that is encoded? Well, this is actually a quite involved strategy, and we are looking at operational model analysis technique and system identification technique. We embed that into a Gaussian process latent force model, which means also that we are going to do some joint input state estimation. What is interesting about this technique is that now we are able to get information when we need it. And in this case, I'm looking at S2, and what we are looking at are the mean and the confidence bounds on the strain response. And you can see that both in the time and in the frequency domain. Now, this is a very effective technique, but we have to make some assumption. We are assuming that we are dealing with linear time invariant models, and this enabled us to do this virtual sensing kind of application. Okay. I'm going to move on to another challenge. As I mentioned at the beginning, I'm very excited about this seminar, so sorry for giving way too many possible information. Challenge 4 is actually dealing with knowledge in terms of discontinuous nonlinearity. Most of the time when we are looking at a system, we don't know what friction model, or for instance, what vibrating path force model should be used. And the main challenge there is that we cannot directly measure that. If you think about a joint, for instance, like in this turbine here, what happens is that to measure friction, we should place a sensor there, but it's not always easy to do so. And so typically what we are dealing with is indirect data that is sparse and noisy. And what we're dealing with are discontinuous non-smooth forces, which means that when we are looking at the response, we might look at multiple motion regime, sharp variation. And if we think about the numerical point of view, these are typically stiff problems. In addition to this challenge, when we're dealing with discontinuous nonlinearity, we are thinking about non-uniqueness. And what I mean by that is that two different friction laws can yield the same response. And this is an example, for instance, shown here. All of this makes solving this problem very complex, and there have been many papers, and these are just few of them, that investigated some of these aspects, but many people have worked in this area for a very long time. What we are interested in is trying to understand and identify the discontinuous part directly from data, knowledge, and physics. So how do we do that? We look at these physics-enhanced parse identification strategies. And pretty much what it says is this. Imagine that you have a system that you can describe in this form, and now you have an unknown functional relationship and a discrepancy bias that is what you know about your equation. So we want to learn something about our system, this function f. And what we have are one set of time series noisy and sparsely collected input-output measurements. What we want is actually an approximation in which what we don't know is going to be approximated by some function multiplied by some coefficient, and what we know that is correct. And what it means is that how do we get this function? How do we learn them? Well, we're going to use a dictionary of function, and by doing so, we're going to have an inductive bias. We're going to say this is going to be actually the candidate function that we're going to use. And we're going to have also an inductive bias in terms of constraints. We know, for instance, that if we are trying to use, if we're looking for obtaining the prediction model with a Runge-Kutta for system, Runge-Kutta scheme, when we are dealing with discontinuous nonlinearity, this will require us to have also an event function defined, which means that this event function should be also based on physics. What I mean by that is that even in when we are thinking about the architecture, we're going to have a learning bias. The goal will be to obtain this sparse coefficient such that we are minimizing this, and this is a sparsity factor. What you see here are the learning bias that is given in terms of the Runge-Kutta scheme, the integration scheme that we are using, but also in terms of the optimization scheme that we're going to use. And we have to think about also how we will get information. Typically, we are getting information, for instance, in terms of displacement, and we have to use spectral method, for instance, to obtain velocity. Now, there will be no time to go through all the approaches, so what I would like to show you is a simple example in which we assume that we have displacement and velocity noisy measurements, we know the linear part, we know the physical constraint, and we have a dictionary of candidate function for friction force that is basically either a dr or a coulomb. The main challenge here is that those will give exactly the same response, and we are generating data in a way that they will give exactly the same response. And what we would like to do is to actually infer back from this measurement, displacement and velocity noisy measurements, what is the correct friction law among this dictionary. And what you see here is when we are generating with the ground truth this, and that's what we are learning. And what we see here is that when we are generating a ground truth, and here you see just the DR law expressed and what we learn. And what we achieved with this was that we were able to identify the correct frictional law in this inverse problem that was very challenging. And we also validated this technique with lab experiments. And what we have done is making a big assumption, because we are assuming that we know the linear part. Now, I'm aware of time and I'm very thankful that you're still here. And I was very excited to tell you a lot about a challenge in SHM. There is this physics for machine learning strategy that is based on a variational autoencoder. I'm going to just briefly mention it. And I hope that you will be interested in learning more through the paper or when asking questions. We start with that. You can see the system here, and you can see that those are very simple systems. And typically, we are having this system, this type of model at the beginning, and we can collect information on measurements point. Now, in reality, this system, when we think about this model can be used to represent something that is real, but in reality, we may have different conditions. And what it means is that our physics knowledge might not be complete or correct, and we cannot use the measurements directly to update this incorrect model because this will give us wrong posteriors. And we would like to do is disentangle the measurements to correctly assess uncertainty the parameters and reconstruct the response contribution. So what we would like to do is basically use something in which we say if we have a nominal physics-based model, but we have a labeled training dataset that is looking at response measurement, domain variables, and class variable, can we now learn how to reconstruct the contribution of the response such that when new measurements come in, we can actually look at it and we have the information about environmental operational parameter measurement. We can now reconstruct the response contribution and carry out regression and classification. Okay, as I told you, unfortunately, I will not have time to go through this, so you're going to see the slide very quickly. Apologies for that, my bad. But what you can see here is what is happening with that, for an example, and what we are very proud of is that we are able to actually reconstruct the response. But we are making an assumption, and there is an additive uncertainty assumption. Again, apologies for not being able to go through it within this seminar. So what I told you during this talk was about uncertainty in SHM and physics-enhanced machine learning strategies. And I show you some of the physics-enhanced machine learning strategies that have been developed within the data vibration uncertainty group. And what I would like to close this seminar with are open challenges and opportunities. And because I told you about many things that we've done, and I told you about what are the things that still need to be done, but there are even more. And these are detecting and removing appropriate data biases, removing physics biases, accounting for noise in the measurements and combine uncertainties, looking at multimodal data, but also how do we do high precision learning from small data set. We should look more into non-uniqueness. I show you just one simple case study. And we have to look also at extreme and out of distribution events and how we can guide decision making and learn things that we didn't know before. Okay. And also, thinking about how to suggest extra data and experiments. Okay, thank you so much for your attention. And I would like to say that dataset codes, lecture notes, and open access paper can be found here. And most of the things that you've seen today would have actually the code and the data available directly on the DV Group website. And I should thank you again for your attention and all the collaborators for working on this. Thank you so much. Thank you.
Thank you so much, Alice. This was amazing. And I think I learned a lot. Maybe I'll open the floor first for the audience, and then probably the host can go forward.
Fantastic.
So anyone from the audience who wants to start this, who wants to have any clarification from Alice?
Cicirello.
I have a lot of questions, but I'm waiting for the audience to see.
Yeah.
People
Because
seem
it was
shy.
very...
We have shy
Yeah.
audience. I think one of us can go ahead. I
Yeah,
also have some questions.
Shovik, you can go ahead.
Okay. So I have 4 questions, but I will limit myself to 3. So this explainability, right? It confuses me a lot. Like when I use ChatGPT, for example, right? It confidently explains wrong thing.
Right? Exactly. Yes.
So then what to do about that? Interpretability is fine. It's a sparse model. You can make sense of the model. So, but
Yes.
explainability is somewhat confusing for me. What if it is explaining wrong thing confidently? So
Exactly.
any thought on that?
And I think it's a very, very good point that you're making. And in fact, sometimes when I talk about this, I say that it's very accurate but wrong, in the sense that your prediction is very accurate, you have very low uncertainty, but you're completely off, you're completely wrong. And it's a very big challenge that we are having at the moment, because indeed, even when we do data-driven techniques, or when we do physics and machine learning technique, we have the risk if we use the wrong architecture, and that's the reason why I was trying to sort of explain all the different sources of problems. We might get something that is very confidently wrong, and that's why I think that we need to develop more validation benchmark, and we have to learn more about the challenges, and it is very, very difficult to tackle this problem. And in fact, that's why I think there is still a very big open area of research.
Yeah, the predictive uncertainty and does not necessarily match with the error, right? In many cases, if it does, that's the best case scenario, but that doesn't happen.
Exactly, and yes, so yeah, it's very interesting, and I know that many people around the world are working towards that, and it's very exciting. Still, many things that we have to learn about that, I think.
Yeah.
Just want to mention one point here, that regarding this, I think this was a very good question that you asked, that whether an uncertainty can capture the error, because sometimes we do want that, but it doesn't capture the error. It does infer the interval, but sometimes even near the errors are so huge that it doesn't incorporate in the band. And I think that I read somewhere that uncertainty is not a replacing of the incorrectness of the model. So if the model is very incorrect, yeah,
exactly. And I think that, and there are, and again, apology. In fact, I had a very long introduction, and then I have to rush through the end. Apologies for that. But I think that most of the time we forget about these aspects, that we have the problem with the physics-based model, or whatever model we are using. We can have a problem with the data as well. And now if you're combining a wrong model, or a partially correct model with the wrong data, and that's typically what we do. And now we are learning something that can be very wrong. So how do we then, and that was the thing about disentanglement, how do we have the data basically split in parts in which we can use part of the data to update the physics, and then part of the data to learn a data-driven part, but the data-driven part is not overtaking the physics. And there actually Jan, there is the one that is leading the paper, the work, came up with a very nice idea in which we have this gradient reversal and bottleneck latent physics latent space, in which we are constraining actually the latent space with physics as well. And this is helping us avoiding this override. And this is very important, because if we are using, again, something that is incorrect, but we are looking at just compensating and not accounting for all the other sources of uncertainties, that will affect our results. So yeah, I told you I'm overexcited about this.
No, I read that paper. I am really excited about the paper, the last one.
Me too. I'm very excited to read that paper.
So the other question is the ambiguity set. That is very interesting.
Yes.
But there is also this idea of non-informative prior, right? So how is it different from the non-informative prior that we use when we do not have any prior knowledge? This Jeffrey's non-informative prior and all of those things are there, right?
Yeah, there are. I mean, robust Bayesian inference has been around for a long time, and typically, when we try to look at ways of dealing with that, and we are looking at ways. Let me turn on the light. 1 second. I realize that I'm very much in the dark. So sorry. 1 second. I'm gonna be faster. I promise you. Here I am back in the light.
Yeah.
Awesome. I think that, the ambiguity set is trying to say we don't want to constrain our choice into a distribution type, and we don't want to specify what is the support. And the support becomes extremely important, because if we say it's a typically we say it's a non-informative prior because it's a uniform distribution. Well, it's actually informative. We are saying which is the support, and and we are saying something. So we can start already by saying, we have a distribution wherever there is, and then we are looking at all the possible distribution that we live in the radius. So we are doing we are using a statistical description now because we are looking at this distance. There is looking at probability distribution basically, and of course there are many of them that we can use, but the Wasserstein, for the reason that I explained earlier, was the most useful, especially because we don't need to have the same support. That's one of the key things.
Right. Actually, that is right. I mean, you don't want to constrain yourself to a prior distribution, right?
Exactly. Because we would like to learn how much that prior distribution assumption is going to affect our posterior, given that in that specific case, as I say, I sort of decided with Felipe, the lead author of the paper, to look at the problem which we had limited knowledge on the prior of our parameters, for instance, the Young modulus or something similar to that, but we also had limited data. And in principle, one can say, if you have lots of data, then it will not matter what was your prior assumption. But the problem is that if you have a small amount of data, everything that you assumed as your prior will actually limit how much your posterior is going to change or vary, or what will be your posterior. So having an understanding of that effect, we believe, is very important, and typically it's another thing that is overlooked. So that's why we went towards that direction.
Okay. And lastly, I think one of the key highlight that I take from this is the is the knowledge, physics, and data. Because the way I used to see is physics and data, and physics is knowledge. But then you said knowledge, physics, data, and then knowledge was like, I guess, mass cannot be negative, those kind of things, or any prior knowledge you have.
And in fact, I use it exactly for that reason, because sometimes, the way in which we talk about knowledge, it can be also in the knowledge of using a certain algorithm. It can be in the knowledge of using a certain model, which is not necessarily, it's also related to a physics-based model that we are building, but it's not necessarily coming directly one-to-one from the physics, if you see what I mean. So by combining that, then I can see the problem, I can see the challenges and the problems I can try to see them in a neater way. So to me, then it's, I think that it's easier to me, and I hope for other people, than to see where are the gaps. Because if I do it in this way, then it comes natural to me again. But I'm not sure if for everyone is the case to see the problems in this way.
It's a very interesting perspective, actually. It's a very interesting perspective that to distinguish knowledge and physics. Physics is knowledge, but it may not with all the knowledge.
Exactly. That's it. Yes. That's it. Yes.
Yeah. So thank you. That's all from my side. I think others will have questions. Rajdeep and Sundatta.
Yeah.
I really hope, yeah.
Rajdeep, you can go for one question. And you're muted.
Oh, yes, people.
Yeah, sorry. So I wanted to ask a little bit about that prior assumption. So I think regarding the ambiguity set. So this ambiguity set, what's the hyperparameter that controls how much you can explore around the nominal prior distribution?
So it's this radius. It's this radius that you have to define, basically. And because we are, in fact, Felipe had this great idea of having this sort of very pictorial thing, which is that this is the probability, this is the nominal probability, and now you're exploring this region. Now, for this analysis, we have to make an assumption, and we assume that we specify the radius. We know how far we want to go. And in principle, you might do it instead of reverse. You might learn also the radius. We thought that for this type of analysis, this was not something that we were interested in. But this is a very important hyperparameter to define, actually.
Okay. And how does it actually, so have you heard of this new thing called generalized Bayesian inference that has come up? I think, so there's something called as generalized Bayesian inference, which talk about the fact that you don't need to have an explicit way of defining a likelihood. You can actually also incorporate a loss as also a kind of a likelihood. And similarly, I think a few people in researchers in in UK, they did this mostly coming from computer science. They said that if you have a Rayleigh prior, so the Rayleigh divergence, and then you can show that the prior sensitivity on the posterior decreases. So that's also a way of trying to reduce the effect of a misspecified prior on the posterior.
Yes,
and they mostly do it for a neural network. because
Yes.
neural networks, they clearly show that we put a Gaussian distribution on the parameters, and it's not necessarily right, especially they're independent of each other and it's zero mean. So that's how they do it. I was thinking, like, so if we were to apply the same kind of thing on a physics, how would that approach and your approach kind of like differentiate? Like, would the two approaches give a result which is so this approach that you proposed is actually is it sensitive to the prior? Like, so if you have a misspecified prior, which is a nominal prior, let's say, it explores all the surrounding regions within that radius and gives you the best one.
Exactly, or looking
Okay,
at the
I
best
see.
and the worst. So that would be the
I see.
difference. I think that those can be integrated. I think that we are looking at two different aspects of the problem, but
Okay.
indeed it can be integrated, and it's very exciting what is going on in that area. So I think that indeed is something very much worth exploring. So we will look more into that. Maybe with
Okay,
you.
so yeah, I mean, that's good to know, because I was trying to think, like, so, okay, you are trying to here explore what is the worst and what's the best.
Exactly.
That explains.
That's
Okay.
it.
Okay. Okay. I
Yes.
see. That's nice. Okay. So yeah, that's my one question. Maybe I'll ask later if there's time. Yeah. So over to you.
Yeah,
I think that we
don't
are
think-
already out of time, so I'm aware that maybe there might be one last question or so, but I am aware of timing. Apologies again for
No
being
worries,
overexcited.
No, I think you pretty much hit everything on time, and we were so excited that we are asking you much more than normal questions.
Okay, nice.
I think I don't see any audience for now who's raising their hands. Is there anyone from the audience who wants to go for a last question?
This is the last chance for now. Raise your hand.
You can send me an email if you want to. I will be very, very
I was going to
happy
say that.
about it.
Otherwise, you have to
Yes.
send an email. So this is
Yeah.
the last chance to ask in person. Otherwise, you have to send an email.
Exactly.
That's what I was going to say. Yeah.
Alice, maybe I'll ask something from the perspective of what we are doing in the group. So we are building something called like hybrid models, where we are trying to constrain the predictions that we get based on the information from the physics-based models.
Yes.
My group doesn't do so much of uncertainty. We are more into the non-uncertainty domain. So I was wondering, like, have you thought about like incorporating hybrid models into your frameworks and seeing how they operate on, like, how much uncertain those predictions are, and how can we capture or how can we like trigger a physics-based model from how erroneous the predictions are?
Yeah, that's a
Like
very
we
good
do an
point.
error
We haven't yet
estimator-based
looked into
approach.
that, and I think that it will be very interesting to go in that direction, especially to look at the bias and the error that come from the physics. At the moment, the closest thing that we have done is this disentanglement, in which we know that our physics model is incomplete and we want to learn something else, basically. We want to learn this data-driven part, but and we want to learn the parameters of this physics-based model. But I think that what you're describing is much more complex and more interesting, to be honest with you. And I will be very interested to explore this more, but I don't have a straight answer to that. It sounds very exciting. And I really look forward to hear more about actually the work that you and your group are doing on that. And I think that it could be, again,
Absolutely.
many opportunities for synergies there. So
Absolutely. I will, once we are ready with our papers, I will definitely send it your way, and then we can have a
super.
discussion offline.
Thank you. Thank you so much.
Thank you so much. And with that, we'll conclude. So thank you, Alice, for this wonderful presentation again. We actually ended the year with an amazing note. So
thank you for saying that. Thank you.
Thank you for tuning in today. So thank you, everyone. And just a small announcement that this is our last presentation for the year. We again start next year with Professor Eleni Chadzi, and we'll keep you posted. So stay tuned and see you next year.